Thank you, everyone. Welcome to the final RSE seminar of Lent term. So this week we've got Louise Brown, who's come down from Nottingham and is going to talk to us about the code she's been writing and maintaining for a while, which is TexGen for materials modeling, but also a little bit about sort of the challenges of being between an academic and an RSE and sort of trying to support these scientific codes on all. So yes, welcome.
Okay, hi. So yeah, today I thought I'm going to give you a bit of software engineering history. I'll tell you a bit about my career, which started a long time ago, and how TexGen has fitted in and how to the RSE community and whatever. So a long time ago, I did a PhD. I did my bachelor's degree at Nottingham in mechanical engineering, and then did a PhD where I developed filament winding machine for threading components like this. There's quite a lot of interest in filament winding at the moment because of the hydrogen storage, filament winding cylinders for storing hydrogen. So I did all of the mechanical, hardware, software design for this filament winding and just sort of a bit of software interest. So off to the side of that picture, there was a PC, and I had the most up-to-date PC in the department. I had a 286, and in those days they had expansion slots, so we created expansion slots with all the sort of hardware that talked to and from the machine and to the robot. Our aim actually was to do non-geodesic winding, so that this is all geodesic paths, but if you can drag the fibre off the geodesic path, then you might get it in a direction that you actually want, that's maybe got the maximum stress and whatever. So the idea was that you put back spots using the robot, pulled it off the geodesic path. Yeah, so it was programmed in C for the main part, all the interpolation stuff, and then we set up interrupt requests, and the control algorithm was in 8086 assembler. So that was a long time ago. After that, I moved to the computer science department, but I actually worked for a company called CAD-CAM Technology, and just sort of from an RSE perspective, right back then, that was 1988, we had an arrangement where two of us worked in the research group, the drawing recognition research group at Nottingham, because we were doing very similar work for the company that we were working for. So we had that sort of arrangement. We actually worked in the research group, but for the company. So what we were doing was early days of image processing, basically. In those days, it was scanned images, there were no digital cameras. So they were scanned images, so you got this file with scan lines, and we developed outlining algorithms to extract the outlines of the shapes. And then what we were trying to do was convert them into sort of stitch patterns, which are what you've got in the middle. So taking the outlines and matching them up into parallel shapes, so you can fill them with stitches like on the right-hand side. Back then, it was DOS, there was no Windows. And the other thing that there wasn't was in DOS, there was no virtual memory system. I'm really giving my
overlays.
Yeah.
So you could overlay memory on something.
So our boss had written an in-house virtual memory system, and when we developed this outlining algorithm, it was paging stuff in and out. So by the time we debugged the outlining system, we'd also debugged the virtual memory system, and they didn't have any problems with it after that. So that was quite interesting. And that led to other technologies. The algorithm we came up with gave you knowledge about which loops were inside each other, and that paved the way for things like laser cutting. And if you look at CAD-CAM technology now, their main business is laser cutters. They still do the software for embroidery, but mainly the laser cutting stuff. So that was after my PhD, and I worked there for 4 years, and then had an unexpected career diversion. My daughter was expected, but 24 hours later being here was not expected. and she had a thing called tracheoesophageal fistula with esophageal atresia, plumbing basically. So the bottom of the esophagus went into the trachea, the top came to a dead end, so they had to cut off here basically and join the two together. So my shortish maternity leave turned into 11 months, and I went back to work for 2 days a week when she was 11 months old. Let's have a happier picture. This is her now. So that sort of career diversion, basically. I went back for 2 days a week, and then my son was born 2.5 years later. And at that point, I thought I can't have a sick toddler and a newborn at the same time. So I stopped work for 2 years. Interestingly, at that point, we had a round of spending cuts. And one of the things I ditched was my IMechE membership, because I said, I'm never going to be a mechanical engineer again. I find myself back there now. So I stopped work completely for 2 years. And then one of the guys from CAD-CAM had set up on his own. And so I spent a few happy years working from home, writing software for home crafts. So my first thing I did was for bobbin lace. We had all these interesting patterns, and you have different shapes that you dragged around. Did one for knitting, did a patchwork one. Does any of you play with hammer beads as children? Making sort of plastic things that you put on pegboards and then iron. So we did a kiddie one version for some software that I wrote for designing hammer bead stuff. So it was all quite fun. And at the same time, I taught clarinet and sax as well. So that sort of kept my sanity, sort of getting out and meeting people as well. And then I did do another job, self-employed, working on sort of OCR for travel documents. Following that, the only image I could find of that had somebody's passport details on, so I thought so that was sort of 13 years. So when lockdown came along, I just went back to the desk that I'd been working at for 13 years previously. So that was no great shock. But then the company that I'd been working for doing the travel document stuff, the funding was pulled and I was made redundant. So at that point, I found myself in a bit of this situation. I was job hunting because of working from home for years. I got a lot of software experience, but not the sort of team leading experience, project management experience that you would expect from somebody with my experience. So I was sort of in this bit of a hole with, you know, like the, how do you square filter into the round hole, or whichever way it was. So I was job hunting for 6 months. And then I saw this advert. Open source software coordinator for advanced textile composite materials at Nottingham, and they were basically looking for a software engineer with a composites background. So I applied for that and got the job. So what I thought I was applying for was a job as a software engineer, and for the first 2 or 3 years, that's pretty much what I did. And the way I was treated was a software engineer developing TextGen. So it's open source software that's was developed at Nottingham. Website there. It was developed in the Composites research group, and it's basically a preprocessor for modelling geometry of textile structures. So think, why do you need textiles for composite materials? So composites, so everybody know what composite materials are? Got a vague idea. I mean, you sort of can go from anything from reinforced concrete to carbon fibre, resin, to ceramic matrix that are used in high temperature for engines and stuff. But basically it's at least 2 materials which combine, and the properties of the overall material are superior to what you have from the individual materials on their own. So typically what's used in aerospace, so things like the Dreamliner, I think they say that's 50% composite now. Lots used in wind turbine blades, various sort of aerospace applications, racing cars made of composites, and still lots of research going on into various uses for composite materials. So why textiles? So basically because a a lot of the time, it's just because they're easier to handle than sort of fibres that have been unidirectional ones that are just sort of sewn onto a background or whatever. So you get things like the one on the left, layers of carbon fibre, and typically they're laminated and made to form a composite material. There's much more research going on into what these ones on the right, which are sort of what we call 3D woven composites, where you get some Z direction through thickness, direction, strength as well. And increasingly looking at different shapes that you can make so that you can have net shaped composites. So I've got a couple of, if anyone's interested. So these are a couple of, I think these are both laminates actually. If you look at the side of them, you can actually see, from the top that they're woven. And if you look at the side, you can just about see the waves of the individual layers. So I don't know if you want to pass them around and have a look. So those are the sorts of things that we're modeling, basically. Because essentially, every time you create a different layup, use a different resin, use a different weave pattern, you've essentially created a new material. So if you're going to then design a component or whatever with that material, then you need to know what its properties are. And typically for woven, they have different properties in different directions. So a metal will have the same Young's modulus, whichever direction you pull it in. These have different Young's moduli, depending on which direction you're putting them in. So you need to know what those properties are so that you can design components, basically. So where does TexGen fit into that? So this is my sort of standard TexGen slide. So essentially, you can model, we use TexGen to model the material on what we call the mesoscale. And typically you model a unit cell because then you can apply periodic boundary conditions and you can predict material properties, Young's modulus, Poisson's ratio, coefficient of thermal expansion, that sort of thing. But it fits into a multi-scale design process because when you have the textile, each of those yarns is made up of thousands of carbon fibres. So they typically anywhere between 3 and sort of standard ones go up to about 24K, depending on the size, obviously. But sort of thousands of carbon fibres in one roving. So we normally do either an FEA simulation at the microscale or use some analytical method to get the microscale properties, and then you feed those into TexGen. So TexGen basically enables you to create textile models. Go into a bit more detail in a bit about how it's sort of set up, and you would typically use that to predict the material properties of the composite. Elastic properties, say, and then you can feed those into your microscale design, to your airframe type scale design. Also, another thing is using just the sort of dry fibre model to do CFD simulations to see how resin is going to pass through. So do permeability simulations, because basically the permeability in the different directions through the composite will be different in different directions. And so if you're designing a mold, you'll be able to mold, put your fabric into a mold, and then you're trying to work out where your inlet puts are and how the resin's going to infuse through it. You need to know how it's going to flow through so you don't get any dry spots. So that's why you want to predict permeability. So that's sort of how TexGen fits in. So on the left-hand side up there, you can see the sort of user interface that you get with TexGen. It's written in C++. The core modeling stuff is written in C++, and then it's wrapped in Python. So it uses WX widgets for the user interface, uses VTK for the rendering, and the bar at the bottom that you can see on the left-hand side there is actually a Python console. So you can either use the user interface to automatically generate textiles or to build them up sort of step by step using the user interface, or you can write scripts. Then there's a run Python button that will then run a script and then display it in the user interface. And then you can use the Python console to interrogate the model you want to execute more of the Python functions, TextGen Python functions, if you want to interactively change stuff after that. So it's reasonably user friendly. I'll show you in a moment how the models are made up, but there are wizards which generate sort of standard type of textiles. And then there's meshing capability, which we'll talk about as well. Just a thought from an RSE point of view, sort of thinking about how users interact. You know, when you're sort of working on software, you're thinking about who's going to be using it and how people use the software. So the code is available on GitHub, but very few people actually download the code and build it. It's a bit of a swine to build. Actually, it takes a couple of days to get everything built and working properly. It's it's not very terribly user friendly. It needs improving. But the vast majority of our users use the Python interface. So they'll use the Python interface to write scripts to build models. So if you want to do anything sort of out of the ordinary, that's not one of the idealized ones, then you would write a script to do it because there's a fair amount of flexibility. So it does tend to be people using it, but I guess the downside of that is that you don't get many people actually contributing to the code. Virtually none. In fact, it tends to only be people from within our group who actually do that. So I don't know what the answer is to that, how you sort of how you encourage people to actually delve into the code. Maybe the C++ frightens them off. It's quite a big piece of code. So that's sort of quite an interesting one, how people use it. And the other thing that they do is you can just run the Python scripts on its own. You don't have to have it through the user interface. So we'll see in a bit. Sort of if you want to run it on an HPC, you can just generate run the scripts, generate a model. You don't have to render it, and then you can use it for whatever you want to use it. And I'll show you an example of that in a bit. So that's TextGen. So just a bit about the implementation. So the core is basically written in C++, as is the export and the renderer, and then you swig to do a Python wrapper so that you can interact with all of the functions via Python. The user interface is WX widgets, and it uses various libraries for things like some of the meshing. The load and save uses XML, so we use only XML to do that. Open Cascade enables you to output to STL for systems and stuff, and then VTK for the rendering. So that in itself sort of raises issues about how do you maintain it. At the moment, we're on a version of VTK, but I've had to download a version because I know to upgrade to the next one, I need to make changes to TextGen, and I haven't had time to do it. So what we really need is some funding to have somebody who can do that. So keeping it all up to date requires people power, which we haven't necessarily got. And as I said, you can use it in various situations, and it runs on both Windows and Linux. So just a bit about how you build TextGen models, what they look like. So essentially, there's a C textile class which contains an array of yarns, and the yarns are just made out of a set of nodes, and there are various interpolation functions which plan the path between those nodes. And then you can specify cross sections along the length of the yarn. So you can have various different cross sections. It can vary along the length. You can specify the cross section at the nodes or at any point in between. So you get a lot of flexibility about what cross section you've got, which is useful for when you're trying to get more realistic models. If you're trying to show how something's been compacted, they don't fall into those nice elliptical shapes. They sort of get squashed. there's a polygon section, so you can actually specify points around the section if you want to. You can do hybrids of different ones. So most of them you can do via the user interface. The polygon one you can only do from a script, and it ends up looking something like. And then basically you then build the yarn. So it uses the interpolation function. Depending on the resolution that you've selected, it splits the yarn into sections along the path between the nodes, and works out what the cross section is at each of those slave nodes. We need a more politically correct terminology, but again, I need the people power to be able to make the change. Haven't got to do that yet. So essentially, you can see this one starts off with a sort of circular cross section and ends up with something that's sort of rounded off square, and it interpolates between the two and gradually changes. So you can have different cross sections. And so typically what you do is you specify the minimum repeat that you've got. So if you've got just a sort of something like a normal shirt, you've got the plain woven thing, you just do literally one repeat like this. And then what we do is specify repeat vectors. So X, Y. So this normally, having specified your minimum amount, you would make the cross section at either end same, so that you get a continuous yarn. But this is just to show you what's going on. They're different at either end. So normally it would form one continuous yarn. But so you can see that this has got an X repeat going here, and then the next one is 5 in the X and 5 in the Y. So that doesn't offset here. So you can imagine if you had another yarn that was in the Y orientation and did something similar, then you would basically get the fabric. And what we then do is specify a domain. So having specified one repeat, got the repeat vectors, and then you say, okay, I want to specify what area of the textile we want to look at. So typically it would be one repeat to do a unit cell, but then some people have done, say, impact simulations for thing with, say, Kevlar. You can simulate impact for body armor, sort of thing. So then you would make the domain much bigger, and you've got a bigger section of the fabric. So it gives it flexibility. Too slowly. So as you saw on the slide with the whole thing about TexGen, you can automatically generate different standard sorts of weaves. So they're all based on that C textile, and then there are various 2D and 3D textile types. So the 2D wizard, which I've just shown you, basically brings up a dialogue. You put in the number of yarns, the dimensions, and then it comes up with a weave pattern dialogue, and you can basically click on those intersections to make your weave pattern. And then essentially what it does is it saves an array of whether the warp or the weft are up or down at each of the intersections, then automatically generates the yarns. And then there's something very similar for 3D yarns. Again, nice user-friendly. There are sort of these 3 or 4 very typical sorts of 3D textiles that you get. So we've basically made a sort of inherited class for each of those. So several pages come up in the wizard for the warps, the wefts, and the binders, the yarns that go through. And then again, the weave pattern dialogue that enables you to specify which ones go up and down at each of the cross sections, and then it automatically generates the textile. And in this case, because you've got yarns that come up and around, it actually adds extra nodes around so that you don't get intersections. And then basically those are all there's a 3D grid that it stores, whether it's warp, weft, or there's nothing there. And then the weave pattern dialogue basically populates that grid, and then it automatically generates the yarns. So what do we do with these models? Well, typically we want to output them to do a simulation. And so in order to do that, you have to mesh. And it's notoriously difficult for textile composites. Just meshing the actual yarns is reasonably okay, because we've got some nice meshing functions for dry. If we're just meshing the yarns, sort of got a nice algorithm that generates conformal meshes. They behave nicely. They're all very well. But the problem comes that when you've got that domain, that's typically what's filled with resin. And so that's part of the material, and you have to mesh that as well. You can see you get sort of, particularly if you're meshing textile that's been compacted, and so you've got weird and wonderful shapes, you get these really thin, slither-like pockets. And it's just a perennial problem of how you deal with that, how you mesh that without going into really, really fine meshes or things that intersect. Sat in my office yesterday with a PhD student talking about, do we need to develop a new method of meshing? So it's an ongoing thing. You go to any textile composites conference and there'll always be something about meshing and how you do that. So it's an ongoing issue. For a lot of cases, just a voxel mesh is okay. So we output a voxel mesh, breaks it up into brick-like patterns, takes a center point, interrogates the model, works out whether it's inside the yarn or the matrix, and designs the properties accordingly. And for things like mechanical properties, that's been proven to work pretty much as well as conformal meshes. But if you're going into the sort of realms of damage, where you've got materials moving past each other, then it sort of get gridlocking and stuff. So it doesn't work so well. So one of my colleagues developed a method of doing octree refinement and then some Laplacian smoothing, which works pretty well. So some applications can use TexGen for unit cell mechanical analysis. This was that orthogonal material, it's what's called orthogonal material, where the yarns go up and down each alternate stack. So this was basically done, was done for the whole composite, but just for clarity to show what's going on, the matrix voxels have been taken out. And then boundary conditions applied and simulations done to predict the tensile stress in this case. And then this one predicting textile permeability. So in that case, the model was created and actually the permeability was done on the voids between the yarns to predict the flow. So that was assuming that they're non-porous yarns. So there's also research going on to what do you do if you take the yarns as being porous? Then you have to take into account the volume fraction, the amount of the yarn spaces that are actually filled with yarns. So it becomes an even more complex problem. And then this is one. So this was actually part of my RSC fellowship. Had a PhD student who was looking at T-pieces. So if you think about these 3D yarns, the 3D textiles, how do you know what structure to do? How do you know which yarns to put, how many layers to have, where you want those binder yarns, what configuration you want them being in? There are a vast number of configurations that you could have. And weavers have sort of come up with things that work, they know things that would drape well, but how do you actually, there's a sort of gap in the design process of how do you actually design one of these thick 3D woven materials to get the material properties that you actually want or need. And it's a black art basically. And then you get these more complex structures, net shaped structures, where you can actually weave. I meant to bring one with me, but I haven't got one. So you basically weave a flat layer of material, but have part of it split so that you can then do a bifurcation. So that's what this project was about. It was, how do you optimize these types of materials? Because the strength of that junction in those two things on the left, one is the one where the yarns sort of cross over, had a much higher pull-out stress to failure than the one where they just split. So the idea was, how can we try and optimize those? And that's sort of so we came up with an optimization framework. So there was project which did this. So this has actually now been made so that it all runs in Python. Started out in MATLAB using the GA algorithm in MATLAB, but now it's uses PyMu. So it's all done in Python. And basically you can set up your optimization problem. You can encode the geometry because of the way that the textiles are specified by in a grid. So you can automatically generate a model, and then run an abacus simulation, calculate objective function, and then your optimization loop. So the complicated thing about that is, or the thing that's difficult about that, is how do you automatically generate large numbers of different models to be able to perform an optimization simulation? So there are various challenges. So for the bifurcation in T-pieces, so if you've woven a piece of material that's flat, how do you then change your model so that it's bifurcated? So that's one. And then how do you make the domain? So the domain that's the resin-filled area, because I forgot to say, when I was talking about the domain, it specifies how large the area that you're looking at is. That was originally specified to be a set of convex planes. But obviously for a T-piece, they're concave. And then you run into problems of it just basically didn't work. So we need to come up with a method of creating a complex domain and being able to mesh that. So I've got a couple of, these are offcuts, so they're not the most fantastic examples, but these are T-pieces. So these have been woven flat, bifurcated, and then resin infused. So essentially, this was sort of process. So this is the weave pattern on the left that gives the instructions to the machine of how to, so the ones and zeros are on a weaving loom, whether you've got the warps lifted up or down, they're the ones that run along the loom. The wefts are the ones that get inserted. So for each of those rows, there's a weft insertion. And so previously I'd written the code that would take the weave pattern and convert it into a TexGen model for 2D weaves. We extended it to 3D weaves, but then you get, if you just apply it straight, you end up with something like this, and you can see it at the middle, they all intersect each other. They just go straight through each other, which clearly isn't a realistic thing. And the other thing to note about this is the binder yarns on the left-hand side there go all the way through. On the right-hand side, they only go through half, which means that you can then split it into 2 layers. And that's where you get the bifurcation. So, George, PhD student, he worked on interrogating that weave pattern, because that gives you information about the order that the wefts are inserted. Those are the ones going across the page in this case. And so we got some micro CT data that told us how they rearrange themselves and the sort of cross sections that you get. So he automated being able to get these sort of rearranged so that they don't intersect. And then we've got a script which performs the bifurcation. So you need to be able to do all of that automatically. And then you need to be able to create the domain. Aware that I'm running out of time. So previously it had been a set of convex planes, but clearly if you've got trying to do something like this, if you're just finding the intersection of the planes, then you end up with multiple intersections and it all gets a bit horrible. So I started trying to write some code for this, and then realized that actually, and then I got sort of partway there, and then sort of thought, well, if you then put yarns inside here, how do you work out where the yarns have crossed over the domain, where you know, how do you cut them off? And I realized that what actually this is a TexGen yarn with 2 nodes, or you could create TexGen yarn with 2 nodes, a polygon cross section with a constant cross section, and then the yarn has all of the functions written to work out where things cross the boundaries and what fits into it. So it's a bit like the thing of the snake going around eating its own tail. So basically, what we call now the prism domain is implemented as a TexGen yarn with 2 nodes, which means that you can have it at various, you can put the 2 nodes at any angle that you want, specify the section. It had to make a bit of an adaptation so that it only used the nodes that you'd said. And miraculously, it does work. So here's the T-piece domain. We've got another guy who's been doing braiding. So he's doing braided cross sections around a circular. So he's created arc-shaped domains by specifying the number of points around and use the prism domain. And as far as I can work out, there are a few people from on the forum who are trying to use it. So does seem to be working. So the upshot is he managed to get the T-piece optimization working. Used the design variables were basically he had a 10-layer textile, so he assigned them the yarn's numbers here, and so the design variable was the order that they end up here. Got it all working, and basically, so these are some of his final results. So this, so that he was doing it to initial failure. So he looked at the global number of failed elements, and when they passed a certain amount, then deemed it to have failed. And this is the progression of the failure. So he ran the optimization and came out with an optimum. So yeah, got the peak load at 30% higher from the best performing to the worst performing. So moving on quickly. So just a bit more, coming back to the sort of career thing and how TexGen has been open sourced. It started out as a 3rd-year project, very, very bright 3rd-year student on the 3rd-year project, who then carried on and did his PhD and developed the version that was released. He and another guy persuaded what was our boss at that time to make it open source, that it would be beneficial, and it was made public, released in 2006. It was sort of dormant after he left. It was dormant for a bit, and then they advertised a couple of times before I came along, and I was funded by an EPSRC Textiles Composites platform grant for 3 years, and sort of worked for 3 years and then another year, and got to that point where I was thinking, actually, by this stage, I'd realized that actually I'm not a software engineer, I'm a research fellow. And I'm supposed to be publishing papers and all this sort of thing, and where's this going, and what am I doing? And then I saw the call for the RSE fellowships, and that was the first I'd heard about the RSE movement or whatever, and read the call for the fellowship and thought, actually, this exactly sums up my predicament. So that was when I applied for that and got that. So that funded TexGen for another 5 years. And the commitment from the university was that I would have an academic post at the end. What they actually said at the time was a non-standard academic post, but because it came in the middle of COVID and that stuff, it ended up being a standard academic post. So, but that's sort of, now there's just me supporting it. But it's, loads of downloads from all over the world. There are people all over the world using it at a time. But the advantage of being open source, so quite a lot of years ago now, we had this company, Voigt. They just downloaded the software, looked and thought, oh, this would do what we need to do. They've got these big paper making machines, and they have these, the roller that you can see there are these really complex textiles, which are very fine weave on one side, which is forming the paper, but has to be quite coarse on where it goes around the roller so that it's hard wearing. And they funded those 2 years to develop this. And one of the advantages of the way that TexGen works is that the deliverable for this project was a Python script with a user interface, which just went to the company. They were the only people who had that script for developing these specific types of textiles. But during the project, we realized there was an issue when we ran in Abacus. There were small intersections in the model. And so I implemented some intersection correction, which actually went into the main body of the code. And it's still there. So there was this sort of nice split between the project develops some code which goes into the open source bit, but that's still deliverable each time. So this is a nice one at the moment. It's been in sort of porous microstructure analysis, PUMA, which is developed by NASA, uses TexGen as their for writing weaves. So yeah, I'm coming to an end. So supporting TexGen as an academic RSE, I still do think of myself as an RSE. It's difficult because at the moment, since September, I've been just swamped with teaching and stuff. And preparing this has been quite nice because it's surfaced TexGen again, and my teaching commitment has sort of gone down a bit. So hopefully I'm going to get a bit more time to think about it. I've got a really good PhD student at the moment who's looking into tapered textiles for things like fan blades. And I have actually got 6 project students working on TextGen related stuff at the moment. It's a bit variable. Some of them have just about managed to write a Python script. Some of them, you know, one guy last year wrote a knit wizard, so you can do knitted textiles, which I haven't actually pulled. It's sitting in GitHub as a pull request that I haven't had time to pull in yet. So so he got stuck into the C++ code and actually did some good stuff. So we keep applying for funding. How do you get funding for maintaining the software? How do I get my VTK to an up-to-date version and have the time and effort to do it? So need to get head around that. But yeah, on the downside, being an RSE as an academic, probably don't meet the traditional KPIs, papers and that, which would affect promotion prospects. But on the upside, I've been teaching MATLAB to 160 aerospace, first-year aerospace students this year, and they're going to submit their project as a GitHub as a Git repo. So they will want Git. So and I'm doing a thing called curriculum transform project. So I'm going to be inputting on for all of our mech aerospace manufacturing what they need to be done by software in practice, and also input into research things. So I've been talking about this. You know, how do we integrate that into the university? How do we get software best practice? So still plenty to do to make it a viable career. So yeah, that's it.
Thank you very much. That was really enjoyable. We've got some time for questions. I know Marion has put in not a question, but a comment which says, can Zuckerberg open source software calls can support existing open source software development? So it's worth looking at those.
Yes.
Otherwise, online or in here, are there any questions?
I'm experimenting this. Thank you very much for the talk. I was looking at this software around one of the biggest challenges in the real world with composites is that you get infections. Is there a way you could use your software to say, look, if you have these types of infections in your system, this is the effect that it'll have in terms of the properties? Or is the software just not set up in a way?
Well, it's very adaptable because you can change the cross sections. I mean, there are a couple of other pieces of software that do similar things, but you can't change cross sections along the length. So that one that I kept on showing of the orthogonal, it has been adapted so you can show that how the fabric compresses. So you could potentially build models which look at the sort of variations. one of the researchers a while ago sort of looked at variability in weaves. So he did a stochastic change in the weave patterns, sort of seeing how they varied to see what difference that made to properties. Voids is a thing that we've sort of mooted the idea of how could we build voids into the TexGen model. Quite got our head around that one. That would be an interesting, but it's one of those things that potentially, if you put the effort into sort of scripting a sort of digital twin thing, isn't it? Sort of trying to create a really realistic model.
Yeah, that's the thing. It's the multi-scale thing.
Yeah.
I mean, when we look at larger scale structures, you cannot model every individual weave. You have to come up with a set of rather system approximates. And so doing analysis using this kind of thing combined with hydrocodes to be able to look at the sensitivity to certain points. But you can then say, okay, these are things we need to worry about, these are things we don't. This is how we can then simplify the data and put it in a continuum type. So that you need to play very carefully with the structure seems to be the focus of TextGen.
And also it's sort of maybe using it like the TP site optimization. We're aware that they're not terribly realistic models, but if you can show that they actually give a good indication of the trends, then you can come up with maybe say a handful of optimal, what you think are optimal configurations that you could then manufacture and test. Because the thing that I forgot to say was to set up a 3D loom, it takes them about a month to set the loom up. So if you can model it, then you've saved a lot of time as well as material. So it might be a sort of, is there a happy medium of coming up with something approaching the realistic that you can home in on them. Yeah.
So I think you've partially identified the solution to the problem you were talking about, the lack of contributors or lack of contributors outside your research group. And you said you thought one of the barriers to entry might be the complex system. Well, I think it's probably the dependencies of the TextGen itself. Is that the case?
Yeah.
Yeah. So would it be possible maybe to set up some continuous integration in GitHub, say, and so that then that would be a hint to people about how to build it? If you copied what the CI was doing for dependencies, then
Possibly. The other thing we were going to try was to get some sort of automated build. So, I mean, that was one of the things we did a proposal for the software for research communities thing, and that was making it more easily buildable was one of the things that we were proposing in that, but we didn't even get the first sift of that. So,
something applications to that.
Yeah, I mean the guy who does the NASA Puma software had said that he would help us to get it on Anaconda and get it so we set it up and build it easily. But yeah, so that sort of thing definitely would be.
I think the spec experts in the room have gone.
But that's another one that's bad, especially if you're running an HPC. That's
I guess Anaconda is probably better for a broader base of contributors. Spec's a bit niche.
So I may have missed. So you said you've got a lot of users, but not many Git downloads. Do you provide kind of a binary?
Yeah. So there's a binary download on SourceForge. So yeah, you can see. I mean, because at the moment that's sitting at over 65,000 downloads since 2006. But obviously there are multiple downloads because there's no release and whatever. So you see spikes after a release. But I mean, it comes up in papers and stuff all over. But people do just download on some. You can tell from the comments that they ask on the forum. So that's another thing I was going to say is that one of the disadvantages of making it really easy to use, like with the wizards, is that people sort of press the buttons and generate spew out a model without really understanding what's going on. So they don't take the time to understand underlying textile and whatever. And then they don't utilize it to its full capacity because they don't realize things like the fact that you could change the cross sections. And
So this is my old PI, who I'm still in touch with. Her biggest trepidation on using code open source is not that people will scoop stuff because it's a complicated code, but it's that people will do junk in, junk out to kind of discredit the model. So have you sort of how this text?
I don't think you get that so much. The really frustrating thing is when you can see a paper with what is clearly a TextGen model.
So I would say
knowledge, but I think generally speaking, the papers that you see that have used it are doing something valid, but not necessarily as much as they could. Yeah.
So I guess my other question I have for you said was, you see papers that come along and use it. One of the big debates in RSE is proper acknowledgement for stuff. So do you have a scientific publication describing TextGen cite back to, or are they citing it in software?
In theory, well, I mean, now we do these, we get so we do that, but virtually nobody uses that. Engineers just don't know about it, or whatever. I'm not sure. And on the downloads page, it says if you use TextGen, please use one of these references to cite it. And some do, some don't. Some still cite Martin Shervin's PhD thesis, which is way out of date. I mean, it's still the fundamentals are still the same, but you know, cite that and then be using the 3D textile stuff, which wasn't. So yeah. So we provide them with all the stuff to be able to reference it, but
You could just make a comment and say, I thought it was a really, really fascinating and really wonderful talk, actually, Louise. And so many things I recognise from it. That sort of model of collaboration with industry, where you sort of separate the IP. And I think we've seen that before with open source software. And this whole concern about intellectual property shouldn't really have to be a problem with open source software at all. I think that's a very good example of it.
yeah.
Also, this whole struggle of keeping your dependencies up to date is something we also struggle with, and you do have to put a lot of effort in to keep that. And I have to really recognise that. Also, the pain of meshing, I also recognise that. So maybe we could have a chat afterwards about some of these things.
Yeah, and I mean, there is still two of my project students at the moment. Over the summer last year, had a guy from a company who made parachutes. Contacted me and said, you know, he's trying to work out the stitched joints parachutes, how they behave. So the upshot is we've got a couple of students doing some feasibility things, which may hopefully lead to a research project. So that's viable. So that's similar thing again.
I think we'll finish up there. And I guess with that, the Lent 2024 season comes to a close. We've got some speakers sort of lined up for next term, so they'll go online once the sort of dates are finalised and everything else. I would say thank you to Zetascale Lab and ICCS for providing some funding for speakers to come and visit. I think that's certainly some of the speakers so far said it's been
cheap
useful.
visitor because I've got a CDRL card.
and also it's reasonably close. So the last thing I was going to say is just thank you once again.